Okay, I think it's time. So, hi everyone, welcome to Lab 9. And for this week, we are going to talk about a hidden Markov model and also how to get access to the TCGA database and also get an overview about the overall NIH TCGA database. A lot of softwares were developed based on this software, based on this database. Well, just a few hints before our lab for this week. You might need the hidden Markov model for this homework 5, and the TCGA data might be related to your homework 6. So a few announcements. The final exam time and location could be found on Canvas. Shirley made the announcement last week. Just do some remind. And also homework 5 is due on this Sunday, and I would hold an additional office hour on each Friday, both last week and also this week. So for this lab, our outline contains first part is the hidden Markov model, and I would introduce you the basic concepts and also some examples about how to use the hidden Markov model in some biological setting, and also how to get access to the TCGA data, which is the second part of our lab. I would take you guys to take an overview of the NIH TCGA database, and also how to get access to the data from TCGA just in the R session, and also how to do the tumor subtype analysis and how to visualize the clustering and PCA. Alright, so before we do so, I just do some quick poll about you guys. How many of you have already go through Shirley's video about the hidden Markov? Maybe not too much. So uh, I would highly suggest you guys to go through the Shirley's lecture before this lab, but just to save your time, I think we could go through them together, and I would make some comments to help you guys understand them better. So let's do it now. So what is hidden Markov model basically doing? We might lead them as she introduced.
Welcome everyone to Statistics 115, 215 class again. And today we're going to talk about hidden Markov model. There are statistical and machine learning algorithms. From the name, they sound so scary and difficult, but once you learn the simplicity and beauty of it, you'll enjoy using it for many problems. And hidden Markov model is one such problem. So let's start. Before we can talk about hidden Markov model, we need to understand what is a Markov chain. IID are independently and identically distributed events. So these are events not correlated with each other.
Well, basically, this part is about the mathematical background about the hidden Markov model, especially about the hidden chain. So the hidden Markov chain actually deals with a time-linked data. So you would encounter them frequently in your research or related one when you are trying to introduce the hidden Markov model. It's fine if you didn't get them all.
So the current event has no predictive power of future event. For example, if some family had a boy, the probability that their next child is going to be a girl is not dependent on the previous child, so it's only the probability of having a girl. The next question, say, if I have a coin and I flip a coin, I got a head, what is the probability the next coin flip will be a head again? We know that as IID process, it's just the probability of having a head, regardless of what the previous coin flip is. The third question example is, if I have a dice, knowing that the previous dice, I got a 5, what is the probability of getting a 1 this time? And you know it's just a probability of 1. And so the previous die toss is not influencing. And so these are independently and identically distributed process. In contrast, discrete Markov process, usually we have a few distinct classes, states, for example, S1, S2, S3, and we have regularly spaced discrete times, like time 1, 2, 3. So a discrete Markov chain are situations where the future state only depends on the present state, but not the past to get here. Which means, for example, in this case, the probability that at time t that we're going to see a particular state, it only, given all the previous states, is only dependent on the probability at the previous one state, one time. And all the previous time doesn't really matter. And this is the probability given by this probability distribution, which is called a transition probability. So I'll show you a few examples in here. By the way, the transition probability of all the different situations need to all be over 0 and less than 1, and they add up to 1. So let's look at some examples. For example, if in, so the states, so this is an exam example. So if somebody in an exam, they passed the exam, in the state will be 1, and if they fail the exam, the state will be 2. And the discrete times will be the number of exams, first exam, second, and third. And the state transition is like this, which means that if they passed one exam, the next chance they will have 80% chance of passing the exam again, but 20% the chance that the next exam they will fail. However, if they fail the exam, the next chance they have a 50-50 chance of passing and failing. And so you can see here, these two numbers need to add up because we know that the previous exam is a pass, and the next one, whether they pass or fail, they add up to all the possibilities. And if they fail the exam, the next exam, whether they pass or fail, they also need to add up to 1. So this is the transition probability, and we'll be using a lot of that. And so let's look at this. Given some student has taken 6 exams for this semester, and their grade is pass, 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 fail, fail, fail. What is the probability that in the next exam the student will pass? And you can see this is given by this probability distribution, which is we're asking what is the probability on the 7th exam the student will either pass or fail, or in this case state 1, which means they will pass, given A is the given this transition probability, and knowing that we have observed 6 exams before where the student has pass, 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 and fail, fail, fail. This, if this is a discrete Markov chain, it would mean that it doesn't matter what the student did early on, the chance that they will pass the next exam will only depend on the previous exam, in which case the student failed. And so we look up the transition matrix. We say, okay, if the previous exam the student failed, they have a 50-50 chance of passing or failing. Therefore, the chance that they will pass is 50%. So that's the first example. The second example of Markov chain is, of course, this is just, we made up this scenario. So the discrete states are, this is a weather example. So one is a raining day, and second is a cloudy day, and the third is a sunny day. And the discrete times is day 1, 2, 3, the weather of each day, the time. And the state transition probability, we're making up this state transition probability, and you can see here every row, they need to add up to 1. And the first row means if the previous day is a rainy day, what is the chance the next day is going to be raining, cloudy, or sunny? In this case, 0.4, 0.3, 0.3. And if the previous day is cloudy, the chance the next day is going to be rain, 0.2, cloudy, 0.6, and sunny, 0.2. If the previous day is sunny, the probability the next day is going to be rain, 0.1, cloudy, 0.1, and sunny is 0.8. So this, again, is the transition probability. And so we have a question here. Given that at day 1, we have a 3, which is a sunny day, the question is, what is the probability that the next 8 days of weather is going to be like this? And so we write it this way, given that in day 1, we have sunny weather, and given this whole transition probability matrix, we're asking the probability of the next 8 days of weather according to this. And this is based on the transition probability as if we know the previous day is a sunny day, the next day being a sunny is a transition A33, which is 0.8 in here. And then so that's the sunny to sunny, and then this another sunny to sunny in here, again 0.8. A sunny to a rainy day is A31 is 0.1 in here. And then rainy to a rainy is here 0.4. A rainy to a sunny here is A13, which is sunny to a rainy to a sunny is 0.3 in here, and A32, and finally an A23. So you multiply these probability matrix, you'll get some numbers here. So that's the second example. The third example is
so until this part, Shirley has already introduced the first object about the hidden Markov model, which was introduced in the Markov chain. Sorry, I didn't get a whiteboard here, so I can just type it in my text editor. And so please remember that whenever you are introduced with a hidden Markov model question, so you might ask some basic elements about the hidden Markov model. And so the first thing might be that you can see from the examples as the states. Yes, where should be the sunny, raining, or cloudy in the second example. And the second one is the transition. So something might transit between these states or within each state. For example, transit the weather from sunny to another sunny day, or transit from the weather from raining to another cloudy day or raining day. So it's called a transition probability. Alright, so that's the basic part about the first object, which is the states. Maybe I should make it the first object. Later, you would encounter the second object, which we called it as the observations. So and also the things that to connect the observations as the emission probability. All right, just the basis for elements with you guys to go through the remaining part of this video. Okay, so now let's go back.
If we have a coin, there are a number of states. Supposedly, we're just trying to use different coins to make different flips. And so supposedly we have a fair coin, and also we have a biased coin or unfair coin. So that's fair coin is F, biased coin is B. The different times is we use a coin to make the flips in here. So these are coin flip 1, 2, 3. And we have a initial probability, which is the probability that the first time we pick a coin as a fair coin is 40%. And the probability that we happen to pick a biased coin in the beginning is 0.6. But we are making up these probabilities. I just want to show you an example. And the transition probability, you can write it as a matrix, but in this case, since we have only two states, we can also use this kind of a diagram to show. For example, if I am using a fair coin, the likelihood that the next time I do a coin flip, I'll use the same coin is 0.9, but then there's 10% chance I'm going to switch to a biased coin. But if I'm using a biased coin, then the chance that the next coin will be biased again is 70%, and then I also have 30% of chance switching back to the fair coin. And so this is the transition probability. And so we have given the transition probability, we can now ask what is the probability that we're going to see the following string of coin flips, given the transition probability and the initial probability. So here, how do we calculate that probability? It's first we have to pick a fair coin in the first place, and then from there we'll go to fair to fair, fair to bias, bias to bias, bias to fair, fair to fair, fair to fair, and fair to bias. And so the remaining ones are all transition probabilities, and you can just multiply their probabilities together and you'll get a number. And so that's the probability given the initial probability and the transition probability. So that's Markov chain. So we talk about Markov chain. What is a hidden Markov model? So hidden Markov model is different in that we still have this coin flip example. There is a fair coin, which is in this case 1, and an unfair coin, which in this case is 2, and we are switching back and forth to do coin flips using different coins. So the coin transition is a Markov chain. However, we are observing, what you are observing here, instead of the coin, we're observing using that coin, we make a coin flip, and we ask, did you get a head or a tail? So in this case, the head and tail is the actual observation. But the states we use, in this case, we're using biased coin to make the flip or a fair coin to make the flip, and so on. So we're using different coins to make the flip. So the probability of a head and tail depends on the coins you use because they have a different probability of giving a head or a tail. The observation of head versus tail is a hidden Markov chain because if we don't tell you the hidden states, so in this case, I'm trying to use a coin to make a flip, but the coin is in my hands and I'm hiding behind the table. Instead, what you can see is I'll just use a coin, I flip, and I'll tell you I got a head. Next time I use a different coin, I'll tell you I got another head. And then I shift between the coins. I only tell you the observation of head, head, tail, tail, head, and so on. I don't tell you what is the coin I'm using. And so the coin state is hidden from the person who is doing the observation. So that's called a hidden Markov model. So what are the elements in a hidden Markov model? Again, let's look at elements of hidden Markov model using the coin toss example. We have a number of states. In this case, the hidden states are the coins we use, which is fair coin and biased coin. We have the number of distinct observations, what we can actually observe. In this case, it can either be a head or a tail from the coin. And then we have another set of parameters. The first is the state transition probability, which is what is the probability of, say, if I'm already using a fair coin, the probability I will use another fair coin is 90%, but the chance I will flip to a biased coin is 10%. If I'm already using a biased coin, I'll have 30% chance of changing to a fair coin, but 70% chance of staying in the biased coin. So that's the transition probability. And we also have this emission probability, which is the probability of giving head or tail given the coin I'm using. So in this case, if I have a fair coin, I'll have a 50-50 chance of giving out a head or tail. But if I'm using a biased coin, you can see it's biased because 80% of the chance I'll get a head and 20% of the chance I'll use a tail. I'll get a tail. And then we have an initial state probability, which is what is the chance that the first coin I pick is going to be a fair coin or a biased coin? In this case, 60% chance I will pick a biased coin in the first place. Okay, so that's the element in a hidden Markov model. What is this useful for? So hidden Markov model is a very useful machine learning algorithm. You can use it in the stock market. For example, imagine there are ups and downs in the market. You observe the stock price going up and down and up and down. But even though there's fluctuations, if we observe the overall trend, if it's overall going up, we know in the market it's called a bull market. But even if individual day there might be up and downs, if overall it's kind of going down, then it's a bear market. It's going to a recession. Right? So despite the daily ups and downs observed, because the big trend of the market is the hidden states of being either a bull or bear market, then we have the observed stocks going up and down. Another example is speech recognition. So in this example, we are trying to say some words or phrases, the actual sentences. So these are the Markov chain. They follow certain rules of grammar, right? Certain words follow other words. The sentence usually have a structure. You have a subject, a verb, and an object. But then that's not readily recognizable by a computer. What the computer sound is taking is the sound that's given. It's heard. Okay, this person said some vowels and consonants, and it's trying to guess what the words are that's hidden from the computer. And so that's speech recognition. Also signal processing. So supposedly we have some people sending a signal over internet. Initially, the signals out is 0 or 1, but this signal might be converted to a analog signal of some values, continuous values, to be sent over the wire. And on the receiving end, because there's fluctuations, we might see some continuous values, and the computer at the receiving end will try to guess, is the original source signal a 0 or a 1 if I receive a signal of, say, 0.8 or 0.9 or 0.98 over a string. So the computer is receiving a signal like this, right? So it's trying to guess, is this 0 or 1? And actually, hidden Markov model is also used in bioinformatics, and we will talk about that after we explain the whole application, the models.
Alright, so that's the basic
Welcome
thing
everyone
about,
to Statistics
okay,
115
we can
215 class
stop
again.
here. So this is the basic introduction about the hidden Markov model and also a brief summary about its application. Well, just to summarize, well, basically you need 4 elements for the hidden Markov model, and the first object is the states, and the transition probability is the connection between 2 states. So it might be the same state, it might also be a different one. For example, changing from a sunny day to still a sunny day, or changing from a sunny day to another rainy day or cloudy day. And the second object of the hidden Markov model might be the observations, and the emission probability is the connection between some specific state to some specific observation. For example, on sunny day, some guy prefers to work. On rainy day, some guy prefer to stay at home and do cleaning. So the connection between the actual activity during some specific day and the weather is called the emission probability. So whenever you encounter the hidden Markov model, just recall these 4 problems. All right, then we would sorry for this type. Then we would talk about 2 questions, which is the actual application of application about the hidden Markov model, and Shelley introduced them in the second video.
So using hidden Markov models, there are 3 problems we are trying to understand. The first problem we try to understand.
Yeah, Shelley introduced the 3 problems, but just the first 2 problems are very important, and also put full point 2 in this homework. So the third, I wouldn't go through the third problems in this lab. If you are interested, her last video is the introduction about the third problem. Okay, so let's go through the first 2 problems together.
Is given the parameters of the hidden Markov model, can we estimate the probability of seeing some observations? The second problem is, if we have the observations, can we guess the hidden states? And the third is, if we don't even have the parameters, we only have the observations, can we estimate the parameters of the hidden Markov model?
Yes, so to summarize these two problems, the first problem might be that you have already know, this is question 1. So question 1 about the hidden Markov model is that you already know the states. How could you infer the observations or the probability to obtain some specific observations? For example, I know the next 7 days weather as sunny, raining, sunny, raining, raining, cloudy, raining. And what's the probability that I observe some guy? I follow this guy for a whole week in the following week. I observe this guy going shopping, 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 cleaning, cleaning, and working and walking. So I want to calculate this probability, and this is the first type of question. And the second type of question is actually used for more settings because it's when we know the observations, how could we make predictions about the specific hidden states? For example, I know I follow a guy for a month, for a week, just for a week, and I know he is doing walking outside on Monday, walking outside on Tuesday, shopping on Wednesday, cleaning at home on Thursday. And how could we make an inference about the weather about through Monday to Thursday, given the actual activities? So this is the second type of question. Actually, it's prediction about the hidden states. But to solve the second part of question, you might need the answer from the first question. Well, this depends on the these two types of algorithms. So now we would go through them in the video about the algorithm to solve these two type of questions. Oh, sorry.
Okay, so let's go to the first problem. And again, we're going to use the coin flip example to explain. So given all the parameters in a hidden Markov model, how do we compute the probability of certain observations? So in this case, supposedly we know the coin, we also know the transition probability and the emission probability. And we ask, what is the probability that we're going to see this string of coin flips? Okay, and to answer this problem, to this question, there are a number of algorithms that have been developed. One is this forward procedure, the other is the backward procedure. So let's explain that. So this first problem is we know the hidden Markov model parameters. We also know that we want to ask what is the probability of seeing these coin flips. So this is a string of coin flips. Supposedly we say, okay, if we know the coins that are used to flip these coins, what is that probability? Okay, you say that, okay, that's easier. So if we know that the first coin flip head is coming from a fair coin, then we say, okay, the probability of head from a fair coin is 0.5. That is the emission probability of a fair coin given a head. And the second one is, now the second one we have a fair coin giving a tail, a biased coin giving a tail, fair coin giving a head, fair coin giving a head, biased coin giving a head, and biased coin giving a tail. And each of them is a emission probability, and you just multiply them together because they are independent. If we already know the coins that's used, of course, it could have been coming from a different path, right? So if we switch these two coins, here is from a fair to a biased, and again, you will get a different probability because now we're trying to use a biased coin to flip this head. And so here you can see the probability become 0.8. And again, in here also, we are trying to use a biased coin to flip this head, which is now 0.8. And so you calculate another probability. So you can imagine for every given pass, there is a probability for observing this coin flip string of coins, right? So what is the overall probability of observing this? You can imagine. So then you ask, what is the probability of using this particular string of coins? And this one we know before. In order to use the first path, we first have to pick a fair coin, which is 0.4. Then we do the transition from a fair coin to a fair coin, 0.9, fair to a biased, 0.1, biased to fair, 0.3, fair to fair, 0.9, fair to biased, 0.1, and biased to biased, 0.7. So that's the probability of using this path of strings, right, the different coins strings. But if we decide to use another path, as we mentioned here, we swap these two fair coin to biased coin, then you can see here, the first coin we picked will be an initial probability of using a biased coin, right? And then the rest is transition, transition, transition. But then the difference here is instead of a fair to fair, which is 0.9, we're using a fair to biased, which is only 0.1. And so you can see that this will end in a different probability. And so every given pass also has its own probability, right? So when we try to understand the total probability of observing a certain string of coin toss, we have to sum over all the possible paths. Remember, there are many, many different paths where you can use different coins we're going to use. And each path will have its own probability given the coins we use in that coin flip to give that particular coin toss probability. And so written out in overall is like this. So if we want to ask, given the parameters, what is the probability of seeing this coin flop is a summation of all the possible paths. First we ask, given the parameters, what is the chance that we're going to use this string of coins. And if we're going to use that string of coins, what is the probability that they give out those heads and tails, right? So you can imagine if we have to sum over all those different paths, it's going to take a very many computations. So for example, for a path of n number of coin flips, and if there are t number of hidden states, in our case, this is the length is 1, 2, 3, 4, 5, 6, 7. So 7 long, and the hidden states in this case we only have head and tail 2 states. There are 2 to the 7th possible paths. But you can imagine if we're looking at stock market, you easily go to a years of market price, 250 market days, and then to decide whether it's a bull or a bear market, this will be an unfeasible calculation. We can't possibly enumerate all the possible string combinations. And so in order to really solve this problem, we use something called dynamic programming. So dynamic programming is that we realize a lot of times we're trying to calculate this big matrix of numbers. Basically, this contains all the possible permutations of the paths. These are the states. And then from each of the states, we need to calculate the observed values. But we realize to get this whole permutation of all the paths is impossible. Therefore, we try to keep track of what result we got from the previous solution before we move to the next step, before we look at the next step in the path. And we try to do keep track of the numbers and do the summations early on and use those numbers in the later numbers. And this can help to speed up the current calculation by keeping track of the previous sub-problem solutions. So let's look at this from the coin flip example. So again, we have the observation that the coin is head, tail, tail, head, 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 tail. And there is an initialization, right? So the initialization is saying that what is a probability that I can use a head to see, I can use a fair coin to see the head versus a biased coin to see the head. So in this case, you can see if I'm using a fair coin in order to get this head, is first I have to pick a fair coin, and then from that fair coin, I also have to give out a head, and that probability is 0.2. But if I have to start from using a biased coin, 0.6, and from the biased coin to get a head, it's much easier, then I get a higher probability. So the initialization is the probability of seeing this particular head from either a fair coin or a biased coin, right? So that's your initialization. Yeah, so you can see here, this number is the alpha 1 from fair coin, and then we do the bias. So the yellow number here is the alpha numbers. If you want to understand what this red dot means, it's in order to see this coin flip and all the coin flips before, what is the probability that this is coming for this coin? I'm using a fair coin or a biased coin. So let's look at, first one is very easy. So let's look at the next step, okay? So we're trying to now calculate this alpha value for time. So this is time 1, now we're looking at time 2, okay? So we know at time 2, we're getting a tail now. So the alpha under this yellow dot on time 2 is asking, so and the top one is asking, what is the chance that I'm seeing a tail now and everything before it in order and use So now we look at time 2. We're asking that if we're now at time 2, in order to see a tail now, plus all the coin flips before that, what is the chance that I'm going to use a fair coin or a biased coin? So these are the yellow dots in here. So you ask, okay, if I'm going to use a fair coin in here, what do I have to do before? You say, okay, well, the previous coin can either be a fair coin or a biased coin. But if I use a fair coin, you can imagine I need to inherit the previous yellow dot because I know this yellow dot means on the top means seeing a head here and whatever before, right? And then from this probability from the fair, I also need to transition now to another fair coin. So it's this yellow dot multiplied by the transition probability from a fair to a fair. Now I'm using the fair coin. But the other probability is I inherit this yellow dot, which says if I'm using a biased coin to see the first head, right? And then I need to transition from a biased coin to a fair coin. And so I need to sum up these two probabilities in here. And now also because I'm using a fair coin, I need to flip the second coin, which is a tail. We need to do a transition probability in here in order to see that second tail, right? So that gives us the second probability. So let's do this calculation. So previously we have the alpha 1 and fair and alpha 1 bias, and now we are trying to calculate. you can see here, from the previous fair coin, I'm now transitioning from fair to fair, plus if I use a bias coin before, I'm transitioning from a bias to a fair. So this is the probability of now using a fair coin now, and then we do a emission probability using this fair coin to give out a tail, which is 0.5. You get a new probability here. Alternatively, so this yellow dot is alpha 2. It means in order to see this coin flip as well as all the previous one, what is the likelihood that I'm using a fair coin in this second coin flip? And this is the probability. But then we can also look at the next, the bottom one. Also, there's a red dots in here. So you can see here, in order here to use a bias coin, I either previously use a fair coin, and then I transition from a fair to a bias. Or I can inherit this yellow dot in here, and then transition from a bias to a bias. And so that's now, this probability is now, I'm using the bias coin. But then from the bias coin, I also need to give out a head. And so I multiply that by the emission probability of giving a head from a bias coin. And so you multiply this probability together, you get a number. And so we can continue this process. And every time we try to calculate the new yellow dot, and that yellow dot means in order to see this particular coin flip, as well as everything before, what is the probability I'm going to use a fair coin now? So you can see here, I inherit the previous yellow dots from fair coin, transition from a fair to fair, or I can inherit the previous bias coin yellow dot. Right, from here, and I transition from bias to fair, and so that's the probability of using the fair coin. But then from that fair coin, I also need to emit a tail, and so that's the emission probability. And so now I get the new alpha 3 being a fair coin. And then alternatively, I can say, okay, so I can use this yellow dot, previous coin being a fair coin, but transition to a bias. Or the previous coin could be a bias coin, and then I transition to I continue to use a bias coin. So this is based on the transition probability. And then now that I'm in a bias coin, I also need to emit a tail from that bias coin. So this is the emission probability. And so now this gives me the number for the new yellow dot in here. And we can continue this process, right? In order to calculate the next yellow dot for alpha 4, it will be this yellow dot transition fair to fair plus this yellow dot transition from bias to fair. And then from this fair coin, I need to emit a head. And so that's the alpha 4 from a fair coin. Alternatively, we can do this. The alpha 3 fair, transition fair to bias. The alpha 3 bias, transition from bias to bias. I add them together, and now I'm using a bias coin. But from the bias coin, I need to give out a head, which is the emission probability. And so you can just keep going. Where is the end? Supposedly this chain just ends right here, but in reality we have 7. We just keep going. And so at the very end, we're asking, what is the probability of seeing a head at the end, in this 4 position? Well, you say, okay, at the end, there are only 2 probabilities. I see this head and everything before, either using a fair coin or using a bias coin. And so we add up these 2 probabilities. And that will be the solution to our problem. Yeah, so you can see at the very end, yeah, you say, okay, I'm seeing a head now, but when I add, so I'm seeing the head, and it either come from a fair coin or a bias coin. So add these 2 numbers, and these numbers have already inherited all the previous numbers before to give me the probability of seeing head, tail, and everything before this coin, right? So that will give me a solution. That is the forward procedure.
So the forward procedure is to answering the first question. So that is given a specific state, what's the probability that we could observe some specific observations. So this is called forward procedure. And then another alternative procedure might be the backward procedure. Actually, we'll talk about that one moment later. And then, when we combine all of them together, we could invent a forward, backward algorithm to solve the second type of question. And we also have a potential one as the right V algorithm. So both of them are dynamic algorithms. And all right, now let's go through them together.
Sure. We can also solve it from backward. So that's the kind of interesting about hidden Markov model. We can solve it from forward. We can also solve it from backward. So backward is we also try to calculate some yellow dots, but now instead of calling them alpha, we call them beta. So the beta one is, if you think about it intuitively, what it means is what is the probability of using this coin in order to see anything after it, but not including the current coin flip? So this initialization is kind of interesting. Initially, we actually don't do anything. We haven't, basically, you already see the last coin flip. There's nothing afterwards. You initialize each of them to 1. Okay, that's the initialization. But then we go backward to see the probability of seeing a certain flip after it using this current coin as being fair or biased coin. So remember, we already have, so basically we're in the time t minus 1 in here. We are trying to ask, we try to estimate these 2 yellow dots in here. This one is, it means in order to see the coin flip after it, what is the chance that now I'm using a fair coin? So in order to estimate this yellow dot, I'm saying, okay, now I'm using a fair coin. But in order to see the coin flip after that, so there are 2 possibilities. One is I am using fair coin now, but the next one I'm going to use a fair coin. And from that fair coin, I give a tail, flip a tail, and then from then on, I will inherit this yellow dot to get everything afterwards. And so that is the transition probability from a fair coin to a fair coin, multiplied by the probability of the emission probability of seeing a tail from the fair coin, and then I inherit whatever is after, right? That's one way. The other way is, right now I'm using a fair coin, but the next coin I'm going to use a biased coin. So you can see here it's a transition from a fair to a bias. Then from this biased coin, I emit a tail, and so that's the new yellow dot in here. And so that's the transition probability, and from then on I can inherit whatever is after, right? And so that's the beta t minus 1 for fair coin. That's this dot. But if we want to estimate this yellow dot, which is what is the probability that at this time I'm going to use a biased coin in order to see all the coin flips after. So you say, okay, if I'm here using a biased coin, I can either do a bias to fair transition, and from that fair coin I'm going to emit the tail, and then from then on I will inherit this yellow dot. The other possibility is, from this, I just use bias coin transition to a bias coin. So that's the transition. And from this bias coin, I emit a tail, and then I will inherit the yellow dot here to get all the things afterwards. So you can see every time we only need to look at one coin after, and then just inherit the yellow dots that we calculated at that step, because that yellow dot will already have summed over all the previous probabilities, right? And so this way, we will get the beta for fair versus bias at the time minus 1. But if we have to keep going now at time point minus 2, we ask, okay, what is the chance that at this time I'm using a fair coin? You say, okay, from here I need to do a fair to fair transition, and from this fair coin I need to emit the head, and then after that I will just inherit whatever this yellow dot is that I calculated in the previous step. Or I can use this fair coin to go to a bias coin. Using that bias coin, I can also flip a head, and then I will inherit this yellow dot to get all the previous numbers. And so you sum over this, right? So that's the new beta t minus 2 for fair coin. I can also do the same for the bias coin. If I'm using a bias coin in here, I could either transition from bias to fair, emit the head, inherit this yellow dot, or I can transition from bias to bias, emit the head, and then inherit the yellow dot from here, and I will sum them up, right? So now I calculate the beta t minus 2, and you can imagine at the end, I keep going. In this case, in order to get this one, it's transition from fair to fair, emit the head, and inherit this dot, plus transition from fair to bias, emit a head from bias coin, and then inherit this yellow dot, and we sum them up. For this yellow dot, it's from bias to fair transition, from fair to head emission, and inherit here this yellow dot. Or we transition from bias to bias, then emit from the bias coin a head, and then inherit this yellow dot. Each of them is a multiplication, and then you add up the 2 possibilities. And you can imagine from this chain, we can keep going backward all the way, to the very end. How do we terminate in this case? You can see here, at the very, very end, we're asking, okay, we have to kind of sum up this last 2. We're asking how to terminate. You say, okay, remember the beta is in order to see this coin, in order to see, if I use fair coin, the probability of seeing all the coin flips after, we're using a bias coin to see all the coin flips after. And so at the very, very end, in order to terminate, we say, okay, in order to see all the coin flips after, we have to either pick a fair coin and then give out that first coin flip, and then inherit the top yellow dot. Or we can use a bias coin, use that bias coin to make the first coin flip, then inherit the yellow dot from the bias coin side, and you add them up together.
So this is the termination for the backward procedure. Within this equation, you can see this pi f and also the pi b is actually the initialization probability. And at the end of the termination, the result of the backward procedure and should be identical to the result of the forward algorithm. So if you compare the result of the backward procedure and the forward procedure, you should expect exactly the same one. That could give you a hint about whether you have to do the right calculation for both of these procedures. All right, so until now, we have already introduced all these elements for this hidden Markov model and also how to answer these two type of questions. So now we already answered how to answer type 1 question of the hidden Markov model, and type 2 question is about given specific observations, how could we make predictions about the hidden states? Well, that's the third part of the video which is talking about. So you can watch the fourth video at home, but I wouldn't go through the fourth one at this moment. I would go through the third video with you guys. This is talking about the type 2 question of the hidden Markov question.
Aircoin. It's actually more used.
Oops, sorry.
In the real-world applications. This is supposedly we have the parameters for the hidden Markov model. We are also given a string of observations. And then the question is how to predict the hidden states, the paths in order
So what Shirley is talking about is actually type 2 question about the hidden Markov model.
to get there. So what is the hidden coin behind each coin flip? It's like this. Okay, so supposedly we have the parameters for the hidden Markov model. And we observed head, tail, tail, head, 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 tail. So the question is, can we guess at this point what is the hidden states that's used, or at every coin flip that we observed, what is the hidden states? Which is, for example, in a stock market, you can imagine you have observed the stock price over a year's time, sometimes going up, sometimes going down. The question is, can you guess? Is January a bull market? February, you guess at each day, are we in the middle of a bull market or bear market, right? It's going up or down overall. And so we are asked to guess the hidden states, right? And so interestingly, problem solution for the problem 1 can now be used to solve this problem 2 using a procedure called forward-backward. So remember, in forward procedure previously, we have estimated all the alpha numbers, right? So what is the alpha numbers? Alpha numbers are the probability of using this coin in order to see all the flips up to now, including the current flip and everything before, right? What's the probability of using a fair coin? So for example, in this case, what is the probability of using a fair coin in order to see ahead and everything before? What is the probability of using a biased coin to see ahead and everything before, right? That's your alpha number. That's from the forward procedure. But we also calculate, using the backward procedure, going backward, we also calculate these beta numbers. What are the beta numbers? The beta number is the probability of using this coin in order to see all the flips after it, not including this one. That's what the beta numbers mean, right? So it's the probability of a fair in order to see everything after, the probability of using a biased coin to see everything after, not including this particular coin. And so now, can we try to guess what is the hidden states, say at this location or at that location? The forward-backward procedure works like this. So instead of calculating a alpha and beta, we now at each location calculate a gamma number. So the gamma number is like this. We ask what is the probability at this location, at the third position, that we are using a fair coin. You can see that's this is the, we're trying to use these numbers to estimate the gamma 3 of being a fair coin. Okay, so this number is basically, we know that we are trying to estimate the third coin being a fair coin, and we say, okay, we have to look at everything before and everything after. And then we kind of multiply them together in order to see the whole string of, based on the whole string of coin flip, I'm trying to guess at this location, what's the probability I'm going to use a fair coin. And so we multiply the alpha 3 fair coin with the beta 3 fair coin, because the alpha 3 fair coin is in order to see a tail and everything before. The beta fair coin here is the chance of using a fair coin to see everything after, right? So now we multiply them together, is kind of the probability of seeing the whole string, divided by what's the alternative, right? So the alternative is at this location, instead of using a fair coin, I'm using a biased coin here. And so if I'm using a bias coin, then the alpha here is okay. In order to see what is the probability of using a bias coin to see a tail and everything before, multiplied by the probability of using a bias coin to see everything after, right? So now that's the alternative. You can see here. This is the fair coin possibility divided by either a fair coin or a bias coin, and these two have to these two basically have to add up to the total possibilities, right? And so basically you just multiply the alpha and beta for fair coin divided by the fair coin possibility and the bias coin probability. So this is the sum of the probability, and you get a number.
So just another interpretation about this equation, we're actually at this gamma, what does this gamma f refer to? Well, at this specific location, we'll add some specific time point, which is time 3 here. So you made a prediction about the hidden state and the f. So this equation, this result, this number, actually is the chances that you made the correct guess, which means the real hidden states is have 65% chances of being correct for that specific loci. And so now, given this specific location, if you already got the gamma for the f, and you observed that it's larger than 0.5, you might predict that, given that you only have 2 hidden states. So now you can make the prediction that at this specific loci, the reliable prediction might be that I would predict it as a fair coin.
And so if this number is over 50%, you're going to guess that at this point, it's more likely to be using a fair coin. And the probability of using a bias coin, the gamma bias, should be 1 minus this number. And you can see that's like a 0.34, something like that. Sorry, 0.44. It's below 50%. Which means if I have to make a guess, I'm going to guess at third location, I'm more likely to be using a fair coin than a bias coin. In fact, at each location, we have a probability estimate. So in some locations, I'm super confident. Say, supposedly the gamma fair coin could be 0.99, but some other locations, even though I made a guess that this is a fair coin, maybe the gamma value for fair coin is only 0.55, then you know that you're not so confident. And so the forward-backward procedure, it can maximize the expected number of correctly predicted states. If we are given a whole string of coin flips, say 200 coin flips using coins that are hidden from the observer, and if the hidden Markov model parameters are already given, and the observers see a whole string like 200 coin flips using this forward-backward procedure, if the observer needs to guess at every coin flip which is the hidden states that this guy used, the forward-backward procedure will ensure that if you do this method many times, you try this many cases, overall you will maximize the total number of correctly predicted states. And so you are more likely to give a correct guess, say 150 times out of 200, right? So or to maximize the number of correct guesses. In addition, at every location, at every coin flip, we have a probability estimate of whether this is a fair or bias coin, so you know how confident that guess is. Remember, in the previous problem 1, we had 2 solutions. One was the forward procedure, and the other was the backward procedure.
Okay, so until now we have already introduced the first method to solve the second type of question, which is the forward and backward algorithm. So how could we know that? First of all, we have to go using the method that we solved the first question to calculate the alpha value and also the beta value. And based on both the alpha value and beta value, we could calculate the gamma value to solve the forward and backward algorithm and to solve the type 2 question. Instead of using this method, we can also use the second method as the Viterbi algorithm. So we'll talk about that at this moment.
Procedure. And they both solved the problem and they gave identical result. For problem 2, in order to guess the hidden states, there are also 2 ways to solve the problem. The first is the forward-backward procedure, and the second is called the Viterbi algorithm. This one also uses the dynamic programming approach, but it's not trying to sum over many conditions. If you think about forward-backward, remember, whenever we're calculating the yellow dots, we're trying to sum over all the previous states or all the states after, doing a lot of summations. Viterbi doesn't do that. So in order to explain that, before we introduced 2 other parameters. One is the delta parameter, which kind of keep track of, is a yellow dot that we try to keep track of things. And then there's a psi parameter, which is a pointer to remember how we got here. So let's look at the Viterbi algorithm procedure in here. So supposedly we have a string of coin tosses, right? And we keep the original initial probability. So let's see here. Initialization. We know that the first coin, so we calculate the delta 1, which is what is the probability of observing a head coming from a a fair coin. So that is, this part is easy. So first we have to use a fair coin. This is the initial probability of 0.4 times the emission probability of using the fair coin to give a head. The delta 1 from the bias coin is if we have to use a biased coin here, multiplied by the emission probability of using the biased coins to give the head, and that's 0.48, right? So that's the initialization. So now we move forward on the Viterbi algorithm. Yeah, so this is the delta 1, and we keep track of these as the yellow dot, which is what is the probability of using this fair coin to see the first head, or using the bias coin to see the first head, right? But then the initial, the recursion is different. Instead of trying to sum over all the different paths, the Viterbi algorithm is actually pretty greedy. It just tries to remember the best way to get here. And it doesn't try to sum, instead it's trying to find the maximum. And so I'll show you how this is done. So in order to see, okay, if I have to get a tail on the second coin, and we try to get the delta delta fair coin. So which means I'm going to use a fair coin here. There are two possibilities. One is the previous coin is a fair coin, and I inherit this yellow number, but then transition from fair to fair. Or if the previous coin is biased, I will inherit this yellow dot, but then transition from biased to fair. And so now instead of trying to sum those two paths together, I do a comparison. This yellow dot multiplied by this transition, compare with this yellow dot multiplied by this transition. I ask, which one is more likely? I only need to keep track of the best path. And so in here, supposedly this one give you a better number. I think it does if you add up the numbers. So this one give me a better path. So the psi is a pointer to remember, okay, this is the path I took. I did not take this path. And so now we know that from here, if I'm going to use a fair coin, that previous coin I used is a bias coin. And so then I just use this yellow dot, use this transition from bias to fair in order to get to the fair coin now. Sorry. And then from this fair coin, I need to use the emission probability to give out a head. Use this fair coin to flip a tail. So that's the emission probability. And so this number multiplied by emission will give me this new yellow dot. And that's the delta for fair coin. In order to calculate on the bottom side, it's this yellow dot, this yellow dot transitioning from fair coin to a bias coin compared to this yellow dot from bias coin, this yellow dot, and the transition from bias to bias. So this number times this, so the delta number times this transition, compare with this delta number multiplied by this transition, and I compare these two, and I only keep track of the best one. And in this case, the side pointer will remember I'm going to use the bottom one, not the top one. And so now that I'm using a bias coin, from here, I need to emit a tail. And so this number multiplied by the emission probability from a bias to a tail, that's my new yellow dot for the bias coin. So the delta bias at second location. Right, so you can calculate the numbers, you can see. And then we keep going, okay? So looking at the third, we're asking what is the chance that we're going to use, or what is the path that will most likely give us the best chance to use a fair coin now in order to give a tail? You say, okay, well, if I'm using a fair now, what are the possibilities? Either previous one I'm using a fair and transition from fair to fair, or previous one I'm using a bias and I'm transitioning from a bias to a fair. Which one is better? I pick the best one. In this case, it's from this yellow dot multiplied by this transition. And now I'm using a fair coin. I emit from this fair coin a tail. And that's my new delta number for fair coin at location 3. We can also calculate the bottom side, which is what is the chance that I'm going to use a biased coin in order to see this tail, or what's the best path to get here using a biased coin here. You say, okay, either I use a fair coin before, I inherit this yellow dot multiplied by the transition from fair to biased, or I use this, inherit this yellow dot, use a biased coin, and then transition from biased to biased. And so you compare these two paths, and you ask which one has a higher number, and I'm going to pick the one that's better. And so I know, okay, I'm going to come from the fair coin to get here, and now that I'm in a bias coin, I need to use this to emit a tail, so that's the emission probability from bias to tail, and that gives me the new delta of bias coin to give the third tail, the third coin flip, which is a tail in here, and we keep going, right? So the delta for this coin flip, if to get here, if I have to use a fair coin to give this head, it's either the previous is a head, I inherit this yellow number multiplied by this transition, compare with if I previously have come from the bias coin, multiplied by this transition, and I compare these two numbers. Whichever is bigger, I'm going to use it, yellow dot transition, to my fair coin now, and from the fair coin, I multiply by the emission probability to give a head, and that's this yellow dot. On the bottom, it's if the previous coin is fair, I inherit this, do the transition from fair to bias, compare with if the previous one is a bias, I inherit this number, I multiply by the transition from bias to bias, I compare the two paths, pick the best path, and then that will give me a bias coin, and from here I still need to emit the head, and that's my new number, okay? And then I just keep going forward and forward. And how does it end at the end? We do something like this. At the very end, we look at the two yellow dot numbers. So it's like, okay, in order to get to this head, I could either use a fair coin or I can use a bias coin. Which of these two numbers are bigger? And oh, you say, this one is bigger. This number is bigger. So I say, okay, then this last coin, I should use a bias coin. But in order to use this bias coin, what was the coin that I had to use to get here? We say, oh, we traverse the arrows, the psi pointers to remember how we got here. We say, okay, in order to get here, the previous coin was another bias coin, right? That's how we got here. And then from here, in order to get here, we trace again the solid arrows. Say, oh, then the previous coin would be a fair coin. And then from there, using the pointers, we say, okay, so the previous one is a bias coin. Therefore, given the current coin flip, the most likely, out of all the possible paths, that single path which will give me the highest probability to give me HTTH coin flip is BFBB. So you can see here the two algorithms, forward backward versus the Viterbi algorithm, even though they try to solve the same problem, the final solution may or may not be identical, because their goals are actually slightly different. Okay, because the Viterbi algorithm is asking, there are many possible paths to give me the whatever the string of observed coin flips. Which one is the path that will give me the highest probability of this particular string of coin tosses? That's the goal. Whereas the forward backward algorithm is trying to guess at each location what is the probability of each node, and its goal is, if I have to make all the guesses of all this node at all the locations all the times, I want to maximize my total number of correct guesses. And so if you try a Viterbi algorithm versus backward and forward algorithm, most of the hidden states you guess are going to be quite similar, but they are not guaranteed to be exactly identical, because they try to optimize a slightly different thing. So that's the second problem for a hidden Markov model, which is if we are given the parameters of a hidden Markov model, and also we have a string of observations, how to choose the sequence, how to choose the paths or the hidden states in order to see this observed sequence of coin flips.
Okay, so up to now, we have already gone through all the basic concepts about the hidden Markov model, and in the next part of our lab material, I would go through the applications about these basic concepts one by one, or also give you some examples.